What happens when you need to collect sensor data across multiple industrial protocols and visualize it in real time? Over 12 weeks, I built this from scratch. 4 sensor nodes using LoRaWAN and Modbus TCP, all feeding into a unified Grafana dashboard. Let me show you how it works. These two are my Modbus nodes. Each one has got a W5500 Ethernet module. They are in turn connected to this Ethernet switch. Each Modbus node has an STM32WL55 temperature and humidity sensor. These are my LoRaWAN modules. They are the WL55JC1. This one is a BME680 environment sensor for temperature, pressure, gas, and humidity. It's also connected to an external battery pack. This is my WizGate Edge Lite 2 LoRaWAN gateway. It's connected to the Ethernet switch. It's also accessible via the Wi-Fi network. I'll show you the live dashboard. Here in Grafana, we have all 4 sensors reporting in real time. Here I have the temperature, that's all nodes, 2 Modbus nodes and 2 LoRaWAN nodes. And then on my right here, I have the humidity, that's for all nodes. And I have the pressure. The pressure, only the BME680, the pressure sensor, and the gas resistance. As for the LoRaWAN, I have the RSSI. I also have the signal to noise ratio. And this is my uptime for my Modbus nodes. And I can go back to 6 hours. And I can also go back to 24 hours. Now for the LoRaWAN signals. The panel shows the LoRaWAN link quality, the RSSI around -15 to -20 dB. That's very strong because the gateway is only a few meters away. In a real-life deployment, you see values like -80, -120. And the signal-to-noise ratio of 12 dB, which is excellent. Let me show you how the data flows. On the left, raw MQTT messages from the gateway. You can see the payload is base64 encoded. And on the right, a decoder script just shows the actual sensor readings, temperature, humidity, pressure, and LoRaWAN signal quality. This is what the bridge does before writing. The Modbus side is simpler. This bridge pulls both nodes over TCP every few seconds and writes directly to InfluxDB. Same tagging scheme, so Grafana treats all 4 nodes uniformly. You see occasional timeouts. The embedded server handles 1 request at a time. The bridge retries to recover, and it does this automatically. The firmware is written in Rust using Embassy async framework. Embassy compiles async code down to a state machine. No RTOS needed. Sensor reading, display updates, and radio transmission all run concurrently, yielding at await points. I ran into a tricky bug. The devices wouldn't join the network, and after hours of debugging, I discovered LoRaWAN transmits EUI's little endian, but I was storing them big endian. So 1 byte reversal later, everything connected. So always verify wire format against the specs. Here's the complete system architecture. Sensors connect to STM32 microcontrollers running Embassy. The LoRaWAN nodes transmit to the RAK gateway, which publish to its internal MQTT broker. The Modbus nodes are powered by a Python bridge. Both bridges write to InfluxDB. Grafana queries InfluxDB for visualization. Everything except the firmware runs in Docker containers. The entire platform, firmware, bridges, dashboards, is in one repository. You can clone it, RAK to Composer app, and have the infrastructure running in minutes. The firmware requires the Rust toolchain and probe arrays for flashing. I also did a stride threat analysis to identify vulnerabilities, an encrypted MQTT, default credentials, that kind of thing. The full security analysis is in week 11 Unified Monitoring repo. This project took 12 weeks of part-time work that involved embedded Rust, industrial protocols, and production data pipelines. All the code is available on GitHub. The link is in the description. If you are working on industrial IoT or embedded systems, I'd like to connect. Drop a comment or find me on LinkedIn. Thanks for watching.